So I think you can agree we've had an amazing morning session. In less than 3 hours, we've heard about the lessons learned from a discovery that changed humankind's perception of themselves, considered the origin of life, and have delved into the unique molecular signatures of life. I believe, by any standard, a productive morning. So our panel will include this morning's speakers, as well as Bengt Nordén, the co-chair of the program, who will help moderate the discussion. So we have a stand-up mic here, and there's a free mic somewhere that you can raise your hand if you have a question.
Can't see a thing.
And if you have a question, please state your name and your affiliation. And for our live stream audience, please ask your questions via Menti. Thank you. So if you have a question, please don't hesitate to come to the mic. Thank you. Oops. So maybe we can start with Dawn. The lights are a little bright here. If you can maybe put them down a bit.
See anybody? I can't see a thing. I do.
What are some of the most important lessons, Dawn, that we've learned from our 3.2 million year old ancestor?
Well, I think some of the important conclusions that we've reached is that we all have a common ancestry. And that's terribly important in this world of deep divisions between cultures, societies, and individuals. We can trace our origins back to a common ancestor to every person on this planet, that we are all Homo sapiens. And we have come here through the same process. I have a feeling that we, with a common origin, need to really think very carefully about a common future. And that we are closely related to one another. And we talk about I talk about being human. The website that I have developed over the years is called Becoming Human, because I don't think we're exactly there yet. We have a long way to go. I also think that, as I stressed in my talk, that when one talks about a creator, we have that evident right here on our planet. And in this last brilliant presentation we heard is that nature is still a great example for us. And when I think about people who have deep personal religious thoughts about a creator and conceive of a creator, I think to myself, why would they be doing to their creator what we are doing to our creator, nature, on this planet? I don't think so. So I feel that 99% of our time as humans, however we define that, has been spent very, very close and as an important participant in the natural world. And we've tended to ignore that. As I said, I don't know if I said that here or yesterday, that there are some anthropologists, when I was an undergraduate, particularly Alfred Kroeber, who thought that culture makes us super organic, beyond biology. And as we saw during even COVID, we are not totally independent of the natural world. We are not super organic. Thinking of ourselves as super organic reminds me of what I sometimes call humanity, and that is Homo egocentricus. We think just too much about ourselves, our own individual. We spend time thinking really in maybe 5 generations, right? And the generation we think of most often is our generation, our parents, our grandparents, our children, and our grandchildren. And we have to begin to think much more deeply about time and our presence on this planet and how we move forward, as I said in my concluding remarks, so that our descendants will look back in appreciation of our having made the right choices.
Thank you. I have a question from the live stream, Xavier.
So this question came for Don during your presentation. Is it possible to find any trace DNA in these skulls, which could be used to make genetic relationship maps?
Could you repeat the question?
Is it possible to find any
So I want-
trace
Is there
DNA in these skulls, which
well,
could be used?
The oldest DNA we have comes from about 700,000 years ago in fossils that were found in northern Spain in the Atapuerca Mountains. They first found DNA, I think, in a fossil of a bear, and there is DNA there. But DNA is very fragile, and only under very specific conditions does it preserve in cave sites, for example. And what's interesting about looking for DNA, we won't find any DNA in Australopithecus, that's just too far back in time. But what is interesting about the use of paleogenetics, spearheaded by our colleague Svante Pääbo, is that it has allowed us to identify for the very first time a species of human for which we have almost no fossils, because DNA can be extracted from the soils of these caves where they lived or from the bones left behind. I'm talking about Denisovans, which were found in Siberia. But we first recognized them on the basis of a tiny little finger bone that was analyzed and produced unbelievably an entire genome. And but you don't know you would never know that was a new species from that little fragment of bone. So DNA in more recent levels of understanding human origins is revealing species that we would never know about. And there's even a species out there that is unnamed because it's got a distinctive kind of DNA. And the DNA found in Neanderthals and sapiens clearly shows us that our ancestors had relationships with Neanderthals, and we carry DNA from Neanderthals in our genomes.
So thank you. Jack, here's a question that came for you. Do you think there's life on other planets? And if so, do you think it'll be similar to life on Earth or completely different?
Yeah. So as I said, I don't know if there's life on other planets, but the question of whether if there is, would it have the same basic underlying chemistry is very interesting. And so far I'd say the evidence from the chemical pathways that lead to RNA kind of suggests that this may be almost deterministic, that given at least a similar environment, the inherent chemistry might lead to life beginning with RNA, which would be, to me, would be pretty surprising. There's this kind of 0-1 large numbers principle, right? If there's one way to do something, shouldn't there be lots of other ways to do it? And I think that's finding those other ways, if they exist, is really a challenge for the field of chemistry, right? We have to actually, to answer that, we have to learn how to make and how nature could have made different kinds of genetic materials. And so I think that's something that we could potentially get to in the future, but we're a long way from that.
Yeah, so I think that's also a question for you, Professor Feringa. How do we learn from Mother Nature to build the smart molecular technology of the future? What should we look for? Where should we go?
Now, what should we look for? This is a fantastic question, of course, because there are too many things to look for. You know, I focused here in my talk a bit on motion, and so that's already quite a challenge, I tell you. But there are so many aspects, you know, and what was mentioned also in earlier talks, you know, the fact that we can replicate, you know, that you can store so much information and then use that information, you know, that we have a brain, you know, the connections, all these connections. We saw the picture of networks, yeah? And this was part of the biological network, you know. This was a small part only, no, that you showed. It's amazing if you look at this kind of complexity of a cell. The cell is more complex, I always heard from my friends in biology, than the whole city of Paris with everything, or New York, you know. So all these interconnected things, you know, all these feedback loops, etc. So we are still often in the laboratories extremely primitive. But getting inspiration from Mother Nature, yeah, from all these different functions, yeah, how is it possible that things assemble, yeah? How is it possible that things can replicate? How can divide? How can you read information? How can you move something, yeah? And all these kind of things is a great source of inspiration. And we are not, and I want to emphasize that, once again, it is, to me at least still, after all these years, so remarkable that Mother Nature uses such a limited set of building blocks, and maybe you have an answer to that, but that we can build a human being or a plant or an animal or whatever with a very limited number of building blocks and atoms, and that makes such a hugely complex system. If you look then at the chemical space, which we have available in principle, it is like the universe, it's endless, yeah? If you count the number of possibilities to make molecules and materials, you know, there is no limit, you know, almost no limit. And I would say that evolution, but of course now the gentleman here can argue with me, we had the natural evolution, but we have, of course, humans have evolved so far that we have now also a technology evolution and other evolutions that are part of the total evolution, yeah? And soon you will integrate this technology with the human being, with the cell. I just read this article by Zenon Bao from Stanford, who makes all these electronics that you can integrate with your body, yeah, like artificial skins, sensors, and all these things. People think of integrating chips in your brain. I think this will be a completely revolution. The question, of course, now the ethical question: do we want that? Yeah. That's another discussion. Yeah.
Actually, Professor Nordén has a response, and maybe Don as well. But we happen to have a filmmaker in the audience who did a film just on this topic. Who I'll ask her to stand up in a minute. Her name is Carrie Bourne. You may have heard of her. But please, if you could go ahead. And while they're responding, I'd like to have some students come to the microphone. Yeah. And if you don't, I'm going to ask the speakers to pick their favorite student from the audience for a question.
So I'm addressing the students now. You have heard three gentlemen present what they think is the truth. And I want to challenge them. They have presented their cases. They have presented explanations that sound sensible, but there remains question marks. And I think you all agree that there is still more to be done. Should I say something here? Ben, you said nature is using chirality. Yeah. If I should be a devil's advocate, which I am sometimes, I could say, maybe it's like tossing a coin. Yeah. It will be either way. Yeah. And if, and this goes back to Jack too, if everything goes back to one event, then you don't need to have the large numbers, distillations that feels the chirality and so on. I mean, there are still pieces in the puzzles that have to be put back.
If I may reflect on that, because you were addressing me, I think this is indeed a great puzzle. And I was at several conferences where I got these questions, you know, and then some of my American colleagues said, God does not gamble. So it cannot be just, or is it just accidental, that's left-handed or right-handed, that we have left-handed amino acids, right-handed DNA. I mean, and it's also not, for me as a scientist, it's not very satisfying, you know, to say, oh, it's just accidental. But who knows, you know, I mean, and then the physics, my physics colleague said, oh, it's the elementary physics force, you know, the alpha particle times 10 to the minus 16. But I've never seen a convincing experiment that proves, you know, that this can be done.
No, it's extremely small, this effect.
I'm not so, who knows? I have not a proper answer there either.
Okay, so if you don't mind, I'm going to take some of the questions here, but at the same time, Oliver, if you have the handheld mic, because some people, okay, we'll start over there. afterwards, but there's some people over here who can't get out of their seats. So go ahead, please.
Hello, my name is Axel, and this question is for you, Donald. How do you think Homo floresiensis integrates with our heritage? Because you didn't mention the species on your presentation.
How does it
integrate? Because it's a lot of countries.
Well, this was a discovery made a number of years ago on the island of Flores, which is right at the end of the Malay archipelago. These are very short hominins, like Lucy. Lucy was only 3.5 feet tall. They don't have terribly large brains. They are making stone tools. And at the when it was first published, people thought that these were probably some sort of a fraud, that they were made up. That how can you have these very short humans way out there as recently as 50,000 years ago? As more discoveries have been made, they're certainly there. They're certainly real. And exactly how they interact on the family tree, we don't know. Some people think that part of their diminutive size is due to island dwarfism, where you have lots of competition for limited resources, and there is selection for smaller sizes, like among a number of these elephants that are found in the Mediterranean islands or off the coast of the western coast of the United States. But it shouldn't have been as big a surprise, I think, because when we have studied lemurs, for example, which are restricted to an island, and that island happens to be Madagascar, and you have lemurs as small as those that fit into your hand, but a big lemur is about like that. Now, on that island, before humans came there and brought about their extinction, there were lemurs the size of female gorillas. And nobody thought that was so much of a surprise. But these are a group of fossils from Flores that are very small. It's not due to some sort of disease. They were selected to be small.
Okay, thank you.
Thank you.
I think there's a question with someone with the mic over here. Could you go ahead?
Yeah. Hi, my name is Elin, and I'm a master's student here at Lund University. And my question is for Dr. Jack. When we talked about, or you talked about the equilibrium between monomers and dimers of the nucleotides, and how you in your lab you're using flow to wash out the imidazole. And I was wondering if this is to sort of mimic or reflect on how it might have happened in nature, or if there are other mechanisms which the equilibrium might have been shifted by either through, for example, micelle formation or some completely other way.
That's good.
Yeah, that's a great question. Thanks. So we've been trying to think of different ways to shift the equilibrium, and there's a kind of interesting feedback between trying to figure out ways in which something might work, and then some geophysical scenarios. So having been to Yellowstone on a field trip, you can see there's plenty of opportunities to have systems in flow, and it's a great way to stay away from equilibrium. So I kind of like the idea that maybe early protocell replication happened in an environment where things were flowing over these cells that might have been stuck to mineral surfaces. But on the other hand, it's also quite possible that there are other ways of doing it, and we won't stop with one. If we can find a different way of doing it, that would be great. We would then have to think of, well, is there a geochemical scenario where that could work? Maybe we'll end up with different possible pathways for solving that particular puzzle, which would be great. We might never know which one actually played the key role, but it would be nice to have multiple ways to understand how that particular difficulty could have been surmounted.
Thank you. At the mic.
Hi, my name is Arian, well, first off, thanks for you all for some very fascinating talks. Is it okay to ask 2 questions?
Yes.
Yeah. So my first question is like a general question. So humans have a seemingly insatiable appetite for discovery. Do you think that we'll ever regret like pursuing scientific progress? Like if you look at discourse about AI or genetic engineering, and like, are we pretending to be Prometheus, or are we just fulfilling a role bestowed upon us by evolution?
Sounds like all of you can perhaps take a stab at that one. Ben, do you want to
No.
start?
I would.
Okay,
I think we would say no. We have to proceed. We need to know more.
No, but this is our destiny, you know, to invent, to discover, to be creative. This is part of evolution, as I see it, you know.
Yeah.
This is why we have our brain. It was mentioned, you know, there is a good reason for it. And it stimulates our brains. And so this adventure of discovery and whatever. And of course, I learned one thing during my whole career, yeah? And that is be modest, because we know so little, you know. There is so much to discover and to unearth. And though they have to, with all due respect for Einstein, in 200 years there will be somebody else and says, okay, Einstein, very nice, but it's not entirely the right theory, there might be something else. And you are very proud on your smartphone, you already know that in 20, 30 years from now, they will say, oh, what is this for old-fashioned technology? Because scientists have discovered something new, you know? And so this drive for invention, discovery, and whatever, as I mentioned, the joy of discovery, yeah? This is a kind of inward passion.
I think maybe what you're getting at is the fact that some of these discoveries can be really dangerous, right?
Yeah.
And can lead to unintended consequences that could be as severe as extinction. You know, going back to atomic weapons, right? So almost every important technological advance can be used for good or bad purposes. So I don't think that's a reason to abandon discovery. It's a reason to be more careful and to have institutions that can try to avoid the bad consequences and emphasize the good consequences.
But if I may add to this, this is also, I'm so happy that you asked this question, because this aspect is really crucial in our education, that we train, yeah, the students, everybody, about these ethical aspects, yeah? I mentioned during my talk, do we want that, yeah? What do we want in the future? And we will hear also about CRISPR-Cas and genome editing. We know all the discussions about genomics, you know, and modifying genomes. This is something we should discuss at our schools, our institutes, at the universities. It's an integral part of our future to discuss about these aspects. I fully agree.
Yeah, but it has to be not just the scientists, right? It
No,
has
no,
to
no,
be
no.
the people
Everybody.
who go into law and politics,
No, no.
who can take discoveries and
No, no.
take them out of our control and use them for
Oh, yeah.
whatever purposes.
I fully
So,
agree.
yeah.
Yes, absolutely.
Thank
Yeah, I think you just simply cannot stop the human mind's quest for discovery, innovation, and gaining more knowledge. We had a very successful film recently about Oppenheimer, of course, about the unintended consequences of that discovery. And at the time, it appeared to be a really necessary step to make. And the point really is that this is a global issue because countries worldwide will be doing their own experimentations and developing their own breakthroughs. But the other thing I'd like to say about what Ben has said is that human evolution is really a synergetic intersection of glacially slow genetic evolution. I mean, we haven't changed a lot since we were hunter-gatherers up to 12,000 years ago. Everybody on the planet was a hunter-gatherer. So it doesn't wipe out 7 million years of natural selection. But at the same time, we are, in addition to genetic change, we are a combination of genetic and cultural change. And cultural change is cumulative. And it is immediately disseminated. And we are at a point in life now where any major breakthroughs that are made will be disseminated immediately. And it is something that distinguishes us, as far as we know, from all life on this planet, our solar system, and maybe the universe. I don't know. But I don't think there should be any brakes put onto scientific research.
Okay. Perhaps because there's other people behind you, if you don't mind just going to the back of the line for your second question. Professor Len, did you have something you want to add? No.
I just want to agree entirely with what was just said.
Okay, excellent. Okay, go ahead.
Yeah. Hi, my name is Ville. I'm from Nösnäsgymnasiet near Gothenburg. I have a question to Professor Ben. How do you determine with the molecular motor travels if one, for instance, would like to travel from one specific point in the body, for example, to another, and not just meaning?
Thank you for the question. Yeah, this is a nice challenge, you know. So you can come to my lab to help us because we don't know. We have not done these motors in the body. We have only used them in cell membranes in the labs, in cells and so. For instance, recently what we did is we used them as a driller to drill a hole in a cancer cell. But to transport something like with our molecular car, this was done in a clean room, you know. With what we call STM techniques, you know. So you can make these surfaces, you put single molecules on it, and then you cannot use a microscope. I'm sure you looked in a microscope at school. But micro is 1,000 times larger. So we have these new scanning probe microscopes. That is, in fact, what you can do is, you have a needle, yeah? And that ends at one atom, and you can see and feel molecules and atoms. And thanks to these new techniques, we can precisely see where the molecules are and how they move, etc. This is one of the techniques we use, yes. But this is all still very primitive. Eh? We have not much control, you know. We are now working on making molecular roads, you know, like in the cell, you know. You have these highways in the cell. Things are transported. For me, it's flabbergasting how Mother Nature during evolution ever evolved these highways in the cell. And it's all dynamic, eh? It's unbelievable. But thanks for the question. This is a great challenge.
Thank you. Okay, next, please.
Sorry. My name is Felicia. I'm a third year at Jensen Gymnasium in Helsingborg. And you were, Mr. Frenga, you were talking about how we're still very primitive with this type of research. And I was wondering what type of potential you think it could have. Like, could it perhaps create like prosthetic arms for people with the help of research in the future?
Yeah, that is now. Well, I was briefly mentioning integrating technology with, So this will definitely come. But then again, the ethical question, what do we want? Do we want to be hybrids, you know, partly robotic, partly human beings, etc.? What will be the future of evolution? And these gentlemen here is much more an expert than I. But what you see now, I mentioned this artificial skin. I see you find it very normal that you have a hip implant or that you get a knee implant or whatever, you know, when you for elderly people. But in the future, people now, I hear these futuristic talks about implanting a chip in your brain. So when you get, you forget a little bit when you get older, you know, like the guys here, like me. Yeah, that helps you a little bit, you know, in the future to remember better. I don't know. Do we want that? Maybe it's very handy, you know. But on the other hand, then there was a question and said, look, can I download you then on internet? Because once you integrate a chip with these brain functions, we have not enough an understanding of the brain functions, I think, to be properly integrated. But anyway, could you then download me on the internet? Eh? And where am I then? Am I in my body or in the cloud? This is all something, you know, that when we talk about the far-fetching future, we have to consider these kind of aspects. But
okay, since this has come up a couple times, Carrie Bourne, if you're in the audience, she just did a movie it's called Cyborg.
Oh, yeah.
And I don't know if she's still here, but if she is, maybe she'd like to come down and make a comment on what she learned. But in the meantime, we'll take the next question.
Just to comment on what Ben was talking about, I was so surprised to learn about the fact that you can take somatic cells and alter them into pluripotent cells and start growing a human brain in a petri dish. And I was at a meeting in Rome, and they're only not much bigger than a grain of rice, but they're now beginning to implant them in sheep brains. And it raises a whole series of ethical questions. Is that a person that's developing? Will that become a conscious being? Will it suffer from pain? And we know that it's beginning to operate like a brain because there's electrical, what do you call them? Just electrical impulses coming out of this artificial brain. And at any rate, that's what I have to say.
So if you don't mind, we'll let Carrie just say a few words about her movie and what she learned,
Wonderful.
and then we'll take the next
Yes,
question.
Absolutely.
Well, hello. My name is Carrie Bourne. I'm a filmmaker from London. I'm so happy to be here. This is the most extraordinarily fascinating conference symposium, and I'm very grateful to learn so much. Yeah, actually, the young man who asked about the Promethean progress, where we're going and so on, was really at the heart of what I wanted to ask you. But for instance, Einstein and his contemporaries, in the 30s, established pugwash. And I wondered whether you think now it's so fascinating to learn about the chirality and the out of equilibrium elements of what you know about nature and so on, and at a molecular level. What do you think on a macro level? Perhaps technology is also now creating a chirality so that we're coming away from nature, that maybe the technology in a way is creating this wave that may be amplified beyond our control. And I wondered whether you think it might be the moment where we need to really consciously take steps to set up ethical bodies. There are some, but they're very slow and bureaucratic through governments. Do you think it's now the responsibility of scientists and artists to come together and educate, as you say, and create sort of ethical bodies, or an international ethical body which can regulate or discuss, or... That's my question.
What are your thoughts?
Professor, yeah, my neighbor here, he has clear thoughts on this.
Yeah, Jack, why don't you start?
There have been examples through recent history where people have tried to do that. I mean, as you mentioned, with atomic weapons, but also with genetic engineering.
Yeah.
So, yeah, I mean, I think it's really important to have people discussing these issues and becoming aware of potential dangers in the future. I think part of the problem with doing that, particularly in AI, is that the work is so large scale and expensive and has such obvious military applications. It's going to be very difficult.
Okay.
I think it would be great if we could do it, but maybe I'm not that optimistic that it will happen.
Yes, I agree, actually. I think it's...
Where will we see this film that you've done?
Well, it's being released later in the year. So
It's what?
It will be released later in the year. I can send it to you if you're interested. But it's about a chap he's the first acknowledged cyborg on the planet, in terms of he has an enhancement, a technological enhancement, which is not strictly for medical purposes. So it takes you into, it's not a pacemaker or a prosthetic limb. It's something which is an addition, an enhancement and an augmentation, which gives him another sense. So the film is about this question of where, in a way, of course, with AI, it's a Pandora's box and it's open and that's it.
And her film, which I had the opportunity to see, takes you into the world of many, especially young people, getting different forms of enhancements, and it's not regulated in any way. So, and apparently quite easy to do. Anyway, thank you, Carrie, and we'll take the next question.
Yeah, I'm Werner from Katedralskolan. I'm a student. Is it possible that I ask discussion question and then take up my thoughts, and then we discuss about it? So the question is it possible that life started in space instead of Earth?
Okay, so I think that there are many good reasons. Well, what do you mean by in space? Do you mean on another planet, or do you mean like?
Yeah, it could be on another planet, or just in the vastness of space. So, for example, in a gas formation.
Yeah, I don't think so. I think there are lots of good reasons for life, at least life as we know it, to happen on chemistry that happens on the surface of a planet. Not in deep sea hydrothermal vents, not in the vacuum, not even on asteroids or comets, but on the surface of a planet. Because you have such a range of sources of energy, physical processes that can, transport, concentrate chemicals. You have everything that you need to do the right chemistry on particular surface environments. Now, with that said, I think on other planets, or Earth-like planets orbiting sun-like stars, the same kinds of things, easily. You can imagine.
I have a comment there. I fully agree, but for a physical-chemical reason, that liquid water must be present. All forms of life involves water. And water, you spoke about the cell layer, the lipid cell layer, the aggregation that the lipids do in the cell layer is due to hydrophobic interactions, where water is an important role, but also in a number of other steps. So that defines the temperature, and it defines also that the water has to be liquid.
But there's an interesting physical-chemical thing, yeah? So there was a group in Japan some 30 years ago, Kubiyota, I think, I probably have that not quite right, who made inside-out membranes. So in a non-polar solvent, you can have membranes where the polar parts are in the middle and the non-polar parts stick out into the solvent. And there are a number of groups we've dabbled in this, trying to make genetic polymers that would work in a non-polar solvent. So I think it's a fun thing to explore. I don't really think there will be weird kinds of life in petroleum lakes, but it's fun to think about.
Yeah. My thoughts on the opinion was that in the beginning, in Big Bang, the temperature was too hot, and now it's too cold. So doesn't that mean that there was a Goldilocks zone where the temperature was between 40 to 20 Celsius?
Yeah.
So, I think it's not right to think of like some uniform optimal temperature. You think of a planet, right, like ours. You can be high up on a mountain or low down in Death Valley, and there's a huge temperature range. Or you can be at the poles or the equator, and there's a huge temperature range. You could have a snowball Earth covered in ice, but near volcanoes, there'll be warm, temperate regions. So the planetary environment gives you a huge range of possibilities for finding sort of clement environments for life.
Yeah.
But you say in space, and you can't exclude life evolving on a comet. I mean, you have one side facing a sun, which is hot, and another is cold, and you could have a microclimate on the comet. So in principle, I don't think you could exclude that this could happen in space.
Okay, thank you. I'm going to take a question from this person who's been holding the microphone for a while. Sorry, I didn't get to you earlier.
Hi, my name is Emily, and I'm from Hvitfeldtska gymnasiet in Gothenburg. And this is a general question for all of you, and it's, will AI play a key role in the research of the origin of different life forms, and in that case, how?
Who wants to start?
I can just say yes. AI is a fantastic tool, and of course it will be used. Scientists will use it, but it will not contain the solution in a simple way. It's just a way to pursue this research.
Jack, you want to add to that?
Well, so there are a lot of aspects to that, but one of the things that's a little bit frustrating about these very large deep neural networks is that it can make connections and give you interesting answers, but you can't understand how it got there, right? This is a huge topic of research, which is to understand how these large networks actually work, how information is stored, how connections are made. I mean, they're designed so that it can happen, but it's hard to actually figure out how something new has arisen. And what we want is understanding, right? We don't want to just know the answer. We want to understand why and how did something work in a particular way. So maybe AI technology will get there, but it's not there now.
Anybody else? Don, do you want to add anything or?
Me?
Yeah.
Well, I plead sort of ignorance about AI in general, but my first experience with AI was the movie 2001, where you had a computer that actually took control of that space station and had its own agenda. And I think that's what most people look at and fear, that we will be under the control of AI. And when I look at, what's the chat one called?
GPT chat.
There's one that you can say, you know, write an essay about something. I mean, that's just plagiarism, as far as I'm concerned. That's how I would define that. But I think that in medical applications, it can be extremely useful. But as this is developing, you know, I don't know what I should read to really help me get my mind around
One
what's
thing you
happening
should do
with
is stay tuned for the rest of the conference, because I think it's going to come up again.
Great, wonderful.
Okay, we have a new question here.
Yeah, so I had a short question for Ben. Do you think that molecular motors could be used for improved, like, controlled drug delivery?
Yeah, absolutely. I think it can be used, yeah, because what we do now is we integrate these motors in capsules, you know, like vesicles or in cell membranes or whatever, and you can use them then to open controlled. And we use them to open controlled nanopores. So what we do is we for instance, we take a protein. I didn't talk about that today, but you take a protein from a spider, yeah, one of these toxic proteins that makes, yeah, pores into cell membranes. We put in these tiny machines there. We engineer genomically, you know, that we precisely know where we want to attach it. And then we can, by light, control the assembly of nanopores in cell membranes. And we use that now recently for putting in the capsule, yeah, inside an anti-cancer drug. Then we irradiate with light and precisely open a single nanopore, and material flows out. And the idea is to exactly treat these tumors, exactly, yeah, without getting all the nasty side effects. This is called photopharmacology, you know, and this is a hot topic nowadays. It's exploding. So precisely taking the new imaging techniques and then write more or less your chemotherapeutic agent or your any drug, you know. Extreme high precision using this tiny precision. Yes, that is the state of affairs at this moment. It's not in the patients, but in the labs itself it works.
Okay, thank you. We're going to take this last question, and then we just have a little couple notes for you, and then we'll head to lunch where you can still ask questions, but we still have much more to the conference with other panels, so you'll have more chances. So go ahead, please.
Thank you. Thanks for all the great talks. My name is Kirill. I'm an organic chemist, work at a local drug discovery company. I remember seeing a report about a study that isobutyronitrile have been found on an asteroid, I think. I was wondering if you could reflect, maybe Professor Shostak mostly, but everyone, on the importance of that kind of find. And maybe, you know, a few words about how are we looking for these things, who is doing that, what does it mean? Because I remember the big deal about that was that it's a branched chain precursor to like a leucine or something, you know. So could it be that, you know, if those things exist out there, that allows us to talk about the probability of forming, you know, meaningful things, but also if these things could come and, you know, fall into the the soup that we had here. Would that mean anything? Thanks.
Yeah. So obviously, meteorite chemistry is a hot topic, especially these days, because now we have the first sample return mission. So we'll be able to get a much deeper understanding of the kinds of chemistry that give rise to the molecular complexity that you see, in asteroids and maybe someday in comets. Personally, my opinion is that what we're seeing is a kind of uncontrolled chemistry in a way. It shows you the kinds of reactions that are fairly easy. They generate a lot of complexity. You see certain molecules that you can tie into precursors of biological building blocks. So it tells you, okay, this kind of chemistry can happen. If it can happen there, it can certainly happen probably on a larger scale on the surface of our planet. So it's kind of encouraging in that way. The amount of material and the complexity of the mixtures, in terms of stuff that actually comes from, on meteorites to the surface of our planet, I think is fairly small, and most of it gets burnt up. So I think the chemistry going on the surface of the planet is larger scale, but we can certainly learn from meteoritic chemistry.
Okay, thank you. And I want to thank you all for listening this morning, and thank you all to our presenters. It's been a fantastic morning.